السلام عليكم ورحمة الله وبركاته. طلاب المرحلة الأولى إن شاء الله زينين. linear algebra 2 linear algebra 2. This is first level lecture 9. Definition. Start with definition. Dimension. What mean dimension? If a vector space V has a basis, basis. Previous lecture we studied basis, which consists of a finite number of vectors. Then we say that V is a finite dimensional vector space. Otherwise, V is said to be infinite dimensional we say that this is infinite dimensional. I repeat definition. If a vector space V has a basis which consists of a finite number of vectors, that means this basis has finite number of vectors. This space has finite number of vectors. Then we say that if basis has finite vector, then we say that V is finite dimensional vector space. Otherwise, خلاف ذلك, is said to be infinite dimensional. Example. R n times 1 R m times n Pn are, this is our examples of finite dimensional vector space. Are finite dimensional vector space. On the other hand, f of r c0 of r and c1 of r, c infinity of r, these are are infinite, infinite dimensional, that means this is infinite dimensional. This f of r, all functions defined on r, and this is continuous function, and this is differentiable function, and this is infinitely many differentiable. This is first order defined derivative first order. This is infinitely many derivative. These are infinite dimensional. Now that just we know what mean finite and what mean infinite. Now we take examples and try to find now this is examples. This is example. Find a basis for the null space of A given below. This is A. A is equal to 1 0 0 1 0, and here 2 2 0 0 1, and here 4 4 4, and here 0 here 0. Find a basis for null space. This is page number 1. And now try to find the basis for null space. Null space that means with equality 0. This is null space. No. Solution. We use Gauss-Jordan elimination to find this. We try to find Gauss-Jordan elimination. 1 0 0 1, and this is 0. Here 2 2 0 0 1, and here 4 4 4. Here 0 0. Try to make this identity. Try to make this is identity. And now 2r1 minus r2, right, in r2 implies r1 the same, 1 0 0 1 0, and 2 minus 2 will be 0. 0 minus 2 is minus 2, and 0 minus 0 will be 0, and here 2 minus 0 will be 2, and here minus 1, because 0 minus 1. And now also 4r1 minus R3 right in R3. This is R3. 4 minus 4 will be 0, and here 0 minus 4 will be minus 4. Also this minus 4, and here 4. This is 4. 4 minus 0 will be 4, and this is 0. So now make this 1 minus 1 over 2 R2 right in R2, the same. Here will be, this is the same, 1 0 0 1 0, and here will be 0. This will be 1, and this is will be 0, and this is will be minus 1, and this is will be half. And now we can make this is also 1 minus 1 over 4 R3 right in R3. This is will be 0, this is will be 1, and this is will be 1, and this is will be minus 1, and this is will be 0. So now just make this 0. That means R2 minus R3 right in R3 implies or R3 minus R2 better is better. R3 minus R2. So this is 0 minus 0. Now this is the same, 1 0 0 1 0, and here also this the same, 0 1 0 minus 1 minus this is half, and here 0 minus 0 will be 0, 1 minus 1 0, and 1 minus 0 1, and this is will be 0, and this is will be 0. So we get this. Zero minus 1, but here maybe no. Oh, here minus 0 will be. Here will be minus 0, because 0 minus half, this is will be minus 1 half. So denote x, denote x is equal to x1, x2, x3, x4 here, and here x5. This is will be x. In the equation, is ax equals 0. Ax equals 0. This is null space. In our example, basis for the null space. Null space, ax equals 0. This is, we call this is null space. And now this is A, and may try to multiply this is matrix with this is quality 0, and here we are substitute here, this is A, get 1 0 0 1 0, and here 0 1 0 minus 1, here half, and here 0 0 1 0 minus half. This is times what this is, x1, x2, x3, x4, x5. This is equal to 0 0 0 0 0. And now we multiply this and get equation. Multiply this by this. What we get? this will be x1 plus x4. This is x4, right? This will be x4, and this times this will be x2 minus x4 plus 1/2 x5, and here this is 0, this is 0, this is x3 minus half x5. This is equality with what? With this is 0, 0, 0, 0, 0, and that means this equals 0. And now we get this is equal 0. That means x1 is equal to x4 minus x4, and x2 is equal to x4 minus half x5, and x3 this is equal to 1/2 x5, and we don't know anything about x4 and x5. This is free variables. This is free variables, so we can, this is, that means x4 is equal to x4, and this is, which can choose any value, and x5 equal to x5. This is for all, x4 x5 belongs to R. This is page number 2. And now we can write these results in vectors form. We can write these results in vector form. In vector form to get the basis for null A. We get x is equal to x. We suppose that x is equal to x1, x2, x3, x4, x5, and x1 we get it, x1 is equal to minus x4 here. x1 is equal to x minus x4, and x2 is equal to x4 minus 1/2 x5, and x3 we equal to 1/2 x5, and this is x4, x5, x5, and substitute here. That means this will be x minus x4, this is x1, and this is x4 minus 1/2 x5, and this is 1/2 x5, and this is x4, and this is x5. And so this is equal to, we can move x4 out, and we get here minus 1, and here 1, and here there is no x4, that means will be 0, and here 1, and here there is no, sorry, so this is 0. This is plus x5, and here there is no x5, this will be 0, and here minus half, and here half, and here 0, and here 1. it follows that the basis for null A is simply it follows that the basis for null A is simply these two vectors, this vector and this vector. First vector is this is minus 1 1 0 1 0, and the second vector is 0 minus 1 half 1 half 0 1. This is basis for null A. This is basis for null A. This is, we call it B. Basis for null A. And now we take another example. Can take another example. Find a basis for the null space of A given below. This is A. Ones 1 2 3 here and 4. This is also 1, and this is also ones, and the fourth one also ones. Sorry, you take easier than this, just 3 4 3. Solution. Try to find R if A. First, we find R if A. You know what R if A? This is 1 1 1 1, and here 1 1 1 1, and here 1 1 1 1. Just we say, write R1 minus R2, write in R2. Also R1 minus R3, write in R3, which implies the first one the same, 1 1 1 1, and here will be 0 0 0 0 0. Also this will be 0 0 0 0, and I can't do anything after that. I can change this. So this is page number 3, and now denote x is equal to x1, x2, x3, x4 in the equation ax equal to 0. This is equation for null space of A. A times x equals 0. This is, we call this is null space. And now we try to find values of x1, x2, x3 times A. This is A. This is A. That mean 1 1 1. This is 1 1 1. This is 0 0 0 0 here, also here 0, all of them, times x. This is x1 x2 x3 x4. This is equal what? Equal 0 0 0 0. 4 times 1. Now we move this. This will be multiply this. This will be x1 plus x2 plus x3 plus x4, and this is this time this will be 0, and also this is will be 0 equal 0 0 0. Okay, now we can write this equal to x1 from this equation. X1 will be equal to minus x2 minus x3 minus x4. This time this and this time. So this is will be okay. This is just 4 4 4 4. Okay, this is just 3 3. Now, and this x2 is equal to x2, and x3 is equal to x3, and x4 also is equal to x4. This is free variables. This is free variables, and this is x1 depends on x2, x3, x4. This is for all x2, x3, x4 belongs to R. We can write these results in vector form. To get the basis for null A. X is equal to, this is x1 equal to minus x2 minus x3 minus x4, and this is x2 will be equal to x2, x3 will be equal to x3, x4 will be equal to x4, and this is equal to here x2 we can, and here will be here minus 1 and here 1, and here 0 and here 0, and the second one plus x3 times vector. This is here minus 1 and here 0 and here 1 and here 0 plus x4 times this vector, here minus 1 and here 0 and here 0 and here 1. So this is vector's basis. It follows that it follows that the basis for null A is simply this set. First vector, this is -1 1 0 0, and second vector is -1 0 1 0, and third vector is -1 0 0 1, and this is B, basis for null space A. This is page number 4. No. And now, sorry, now I think now we can take some propositions and definition. Now take this definition. If V is a finite dimensional vector space, then the dimension of V is the number of vectors in any basis for any basis of, we say that, of V, and it is denoted dimension of V. This is abbreviate dimension. If V a finite dimensional, if finite dimensional vector space, then the dimension of V, there is dimension terminology, dimension of V is the number of vectors in any basis. Number of vectors in any basis for V, this is dimension of V. Dimension of V is number of bases of V. Okay, now take example. Let example, dimension of R n times 1 is equal to n. This is n. And dimension of Rm times n is equal to mn times n times n. And this is n times 1 is n, and here n times m. And this is a proposition. Now we take this as a proposition. Suppose V is a vector space with dimension V is equal to n. Dimension V is equal to n. Number one, if S is a set with more than n vectors, then S is linearly dependent. Number two, if S is a set with less than n vectors, then S does not generate V. This is a proposition. What mean? If V is dimension V equal n, then if S a set of more than n vectors, more than the dimension, that means more than the bases, then S is linearly dependent. And if S is a set with less than n, less than number of vectors of n bases, then S doesn't generate V. That means S not span V. This is without proof. And this is without a proof. Second proposition, this is page number 5. Also take this as a proposition. Let V be a vector space. A vector space, and suppose S is a non-empty set. Of vectors in V. Number one, if S is linearly independent a non-zero vector V doesn't belong to span S, then S union V is a linearly independent set. And 2, if V belongs to S is a linear combination of other vectors in S, then span S minus V equal to span S. What means this proposition? If V vector space, suppose S non-empty set. S, this is non-empty set of vectors in V, the subset of V. If S linearly independent, a non-zero vector V doesn't belong to any vector, non-zero vector, doesn't belong in a span V, then S union V will be also linearly independent set, because this is V doesn't belong to span S. So if we add this vector to S is still linearly independent set. And now too, if V belongs to S is a linear combination of other vectors in S. Now the opposite. If V belongs S, a linear combination of other vectors in S, then span S minus V will be equal to span S. It will be the same. Span of these sets will be the same. And now this is proposition. This is also that to prove proposition. Let V be n-dimensional vector space with dimension n. A set S with n vectors is a basis for V if S is either linearly independent or if span S is equal to V. You remember we say a set is basis for vector space V if this set satisfies two conditions. First condition will be linearly independent and span S will be equal to V. We have to satisfy these conditions, two conditions, linearly independent and span S equal to V. Now in this proposition, if let V be n-dimensional vector space, this is with n dimension, that means the number of elements in bases will be n. A set S with n vectors satisfy n vectors, the same dimension of V. If 2, this is 2 vectors. If 3, this is 3 vectors, and so on. If this set has the same dimension of V, then then this set will be basis for V. Will be basis for V if S either linearly independent or span S equal to V. That means we need just satisfy one condition. Either satisfy S linearly independent or satisfy S span S will be equal to N to V. Will be equal to V. This is important. This is proposition, and now we take this is proposition also. Proposition without to prove, just proposition. If V is a finite dimensional, is a finite dimensional vector space and W subspace of V, W is subspace of V, then dimension of W less than or equal dimension of V. Moreover, if dimension of V is equal dimension of W, then V equal to W. If the same dimension, so this will be, there is equality if they are the same dimension. I think this is enough for today. Thank you very much. Goodbye.